Hello everybody, welcome back to another Gregorius Maths video. Today I'll be doing another abstract algebra video. Abstract algebra 1.2. Spoiler alert, we're going to be doing Caley tables. So for any computer scientists watching this, this will probably become familiar to you, and then you'll say, hey, abstract algebra is cool, and then we can all be friends. Anyway, this will include a quick note about homomorphisms, but then I thought, hey, why don't I just do a video on Caley tables, and then include the note, because, you know, why not? So, okay, let's just, what am I saying? Let's just prove something quickly about these Caley tables, okay? So if we have a quick example, say we have some operation, asterisk, okay? We have E, we have A, we have E, we have A. E is the identity element, so that means E asterisk E is E. E asterisk A is A, E asterisk A is A, and A asterisk, you know what I mean, is actually E, okay? And here's why, okay? All of the Caley tables, that was an example by the way, that was a quick example. None of the rows or columns can have, okay, let's write this. None the rows or columns of the Caley table can have the same element. Okay? Again, this computer scientists, you might not recognize this, but this, I'm pretty sure this is helpful in computer science, okay? These Caley tables. Okay, and anyway, let's just prove this, okay? Say we have some Caley table like this. Okay? We have some thing here. We have X. We have Y. We have some other stuff. We have some other stuff. Okay? Now, okay, let's just call this A. Right? Let's just call this B. Okay? Now let's assume that Z appears here and here. Or equivalently, X asterisk A equals B asterisk. I'm just going to say times because that's so much easier for me. Asterisk A, okay? Okay, because X and A, this is the operation. X asterisk A equals Z. But then B asterisk A equals Z, okay? Now multiply both sides by A inverse, okay? Now, because these are both associative, this means that X times A inverse equals B times A inverse. And that means that X equals B. Contradiction. Okay? That's contradiction because X and B are not the same. And therefore, we can say QED on this one. Okay? That was just a quick proof. And now, a challenge for you guys is to just use the exact same reasoning but flipped to prove that the columns the rows can't have the same element, okay? It's the same thing just with the rows. You just do nothing different. Okay? Tables. Well, none of the rows of Caley tables have the same element. Okay? I'm going to keep this on the board. Now, let's go back to our example, which we had earlier. We had our little thing here. We had our E. We had our A. We had an E. We had our A. So E asterisk E is E because it's the identity element. Again, A. A. And now because we would, if this were an A, then the column and the row would have the same element, so that can't be. So therefore this must be E. And it turns out that this is some fancy jargon coming up here. This is isomorphic to the integers mod 2. Okay? Under addition. Because if we draw out this table, plus E is 0, A is 1. So this is a bit like binary, I guess. 0, 1. Okay? 0 plus 0 is 0, mod 2. 0 plus 1 is 1, mod 2. 0 plus 1 is 1, mod 2. 1 plus 1 is 0, mod 2. Why is 1 plus 1 0? 1 plus 1 is 2. And mod... Okay, so any even number is congruent to 0, mod 2. Because when you divide it by 2, it leaves a remainder of 0. That's just what this mod 2 means. Okay? And now if we compare it to this, E, all of the E's match up and all of the A's match up. Which means that these two are isomorphic. Just means the same thing, basically. I'll go more into detail of some properties of isomorphism soon. Okay? And now, this is a bit like Sudoku, okay? So that's why I don't know much about computer science, but that's why I think that this just looks a bit computer sciencey to me. So let's do the group of order 3. This was a group of order 2, or this equals 2. Okay, if this is G, it looks like an absolute value, it just means that it's a group of order 2. And we have E, A, B here, okay? So again, I already said, this is like Sudoku. Except we can fill out these two rows. E, A, B, E, A, B, okay? Because this is the identity element, so it doesn't change anything, okay? Now, what's A times A? Well, it can't be A, because that would be a contradiction, like we've already proven. So let's see what happens if it's E. That would mean that this is B, but that would mean that that row has 2 of the same element, which is not good. Therefore, this must be B, and this is E. Okay? Now, again, this is B, E, this must be A. Okay? And now, therefore, B times B is A times B must be, this is A, this is B, A times B must be E. A, E, okay? So this is, again, this is isomorphic to the integers mod 3. I don't remember if I'm getting this notation right or if this 3 should be here. I'm just going to give myself the benefit of that. Because if we quit, like, under addition, again. Okay? If we draw out the Caley table for this. E, A, B, E, A, B. Oh, what am I doing? 0, 0, 1, 2 is what I meant. But I'm dumb. 0, 1, 2. Okay? 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. And we can do the same thing here. Now, what's 2 plus 1 mod 3? Well, 2 plus 1 is 3, but 3 divides exactly into 3. So this is 0 mod 3. 2 plus 2 is 4. Minus 1, that's 3 quick maths. 2 plus 2 is 4. So what's 4 mod 3? Well, 4 mod 3, so what's 4 divided by 3? That is 3 with a remainder of 1. So this is 1. 1 plus 1 is 2. That's 2. 2 plus 1 is 0, as we already said. Okay? And now if you compare these two in your head, or however, I'll leave these two for a second, just to take that in. These two are exactly the same. And now, here comes the quick note about homomorphisms. Okay? So, let's just do this, okay? So now, if you want to compare two groups with a we want to compare them, okay? And the way we can do this is, of course, with a homomorphism. But in general, okay, so say this is G, okay? This Caley table is G. It has A, it has B, it has X, it has Y. And whatever, it has some stuff on here. Okay? Oh yeah, it must have E as well. And let's say that this here is just X. And we want H, okay? This is Y. This will be X. Asterisk Y. Okay, we'll just say that this is some random stuff. Okay, this is also random stuff. This is X asterisk Y. Now we want a function that maps it onto H. Okay, we want a function that maps this X cross Y onto this Caley table, which represents H. Okay. Okay, and now this will, as you'll see, this will just make the definition of a homomorphism. We have some stuff. We have f of x here and f of y. And we have some columns, whatever, blah, blah, blah. And now we want a function from G to H. Okay? We want it such that it maps this onto this. Okay? This function will map f of x, x has times y, to f of x times y. However, this is also equal to, oh yeah, this is some new operation. Let's just call it diamond. It can be anything, because H has this other operation. Diamond and asterisk can be the same, no problem. But let's just say that they're different. Okay, this is also equal to f of y diamond f of x. Or whatever, f of x diamond f of y. And that's literally the definition of a homomorphism. It's just a function from G to H such that f of x star asterisk y equals f of x diamond f of y. Okay? So let me just give you a quick note. So when these two are different. So if we have G, okay? Oh, by the way, computer scientists, comment down below if this Caley table stuff will be useful in computer science. I'm pretty sure it would be. Okay, if we have G, which is all of the real numbers under multiplication, and we have H, which is all the real numbers under multiplication, the positive real numbers under multiplication. These are both groups you can check. You can check this. Okay, this has an identity element. Is it associative? And does each element have an inverse? Check for both. You'll find that they're both groups. And now we'll define a function f from G to H such that f of x equals e to the x. Equals e to the x. Okay? Now, is this a homomorphism? Yes. Why? Does f of x plus y, so does f of x plus y equal f of x, diamond in this case is times, I'll just do a dot so that we don't confuse with the x's, f of y. Well, let's plug this in. That would imply that e to the power of x plus y equals e to the power of x times e to the power of y. Is this true? Yes. Therefore, that implies that I don't really need to write this, I just need to write f is a homomorphism. And that was my quick note about homomorphisms. Just a little bit of motivation as to where this definition came from. And that's it. I'm not sure what I'm doing. Goodbye.